So, when you think about AI, what year pops into your head? 2020? 2010? How about 1958? Yeah, it's pretty wild, right? Today, we're going to dive into this incredible paper from way back then that literally sketched out the blueprint for the thinking machines all around us today. See, back in the 50s, this question, could a machine actually think like a human brain? That wasn't just science fiction. It was a real, honest-to-God scientific challenge. People were seriously asking, can we build something that doesn't just calculate, but, well, thinks? And then, in 1958, this one scientist, a psychologist named Frank Rosenblatt, comes along with this just radical blueprint. He called his machine the Perceptron. And it was his big swing at trying to model how our brains might actually learn. So, to really get what he was building, we've got to first understand how he thought we think. Okay, first up, how does the brain even learn? Rosenblatt knew that cognition is this giant, messy mystery. So he did what great scientists do. He broke it down. He said, look, any thinking system, whether it's us or a machine, has to deal with three basic questions. First, sensing. Simple enough, right? How you get information from the outside world into the system. But Rosenblatt was like, yeah, okay, that's step one. But the real magic, the big mystery, is in steps 2 and 3. How do we store that info? And then how do we actually use it to recognize things and, do stuff? He felt like everyone was just guessing at that part. Which brings us to the two big theories of memory at the time. The scientific community was basically split right down the middle on this one. So you had two camps. On one side, you've got coded memory. Think of your brain like a perfect photo album or a filing cabinet. You see a cat, you file away a perfect cat picture. To recognize a new cat, you just flip through the album and find a match. But then there was this other idea, the connectionist theory. This one's totally different. It says memory isn't a thing you store at all. It's a new path you forge, like building a new road in a city. The more you use that road, the wider and faster it gets. And Rosenblatt? Well, he planted his flag firmly in that second camp. He went all in on the connectionist idea. He was convinced a machine could learn, not by storing perfect pictures, but by strengthening some pathways and letting others fade away. For him, recognizing something wasn't a separate search and match process. Nope. It just happened. It was the natural result of information flowing down those well-worn paths. All right, so that brings us to the perceptron itself. What exactly was this thing, and what made it so new and different? Okay, this is what's so cool about it. Instead of being built on precise, rigid logic like a normal computer, the perceptron was all about probability. It started out as a total mess, just a bunch of random connections. But, and this is the key, it was plastic. It could change. The connections could get stronger or weaker over time based on experience. So it wasn't about programming it with rules. It was about letting it learn to group similar things together by building its own pathways. I mean, for the 1950s, that was a mind-blowing concept. So the big question is, if you start with just a random jumble of connections, how on earth does it learn to do anything useful, like see patterns? Let's walk through it, because this is where the genius of the whole thing really shines. Okay, imagine it in 3 steps. First, you've got the S points. Think of this like a super simple retina on a camera. It just detects a pattern, say a square. Now, these S points are wired up totally randomly to this big middle layer of A units, or association units. When the S points see the square, a specific set of those A units fires up. Finally, all those firing A units send their signals on to the R units, the response units, and their job is to make the final call. Yep, that's a square. The whole thing is a one-way street. Input, processing, output. So how does it get smarter? The secret sauce is this idea Rosenblatt called value. Here's the best way to think about it. It's like a volume knob. Every single time the network gets an answer right, it reaches back and turns up the volume on all the A units that help to get that right answer. Their signal gets stronger, more influential. You do this over and over, and pretty soon, the pathways that lead to right answers are like superhighways, and the ones that lead to wrong answers are just quiet country roads. So the training process is pretty straightforward, really. You just show the machine a square. If it guesses square, you reinforce those connections. Then you show it a circle. If it guesses circle, you reinforce those connections. You just do this again and again and again, thousands of times. But here's the million-dollar question. What happens when you show it a totally new square, one it has never, ever seen before? This is the moment of truth. Now, Rosenblatt's paper has a bunch of math, and you get quotes like this one. Don't let the fancy words like asymptote scare you off. All this is really saying is something absolutely incredible. It means that after enough training, the machine gets just as good at recognizing a brand new square as it is at recognizing the same old squares you showed it over and over. Let me say that again because this is the whole point. After enough training, it could correctly identify a square it had never, ever seen. This is called generalization, and it is like the holy grail of learning. The machine wasn't just memorizing photos of squares, no way. By strengthening all those little connections, it had actually learned the idea, the very concept of what makes a square a square. Okay, so this thing was clearly powerful, but what could it really do? And just as importantly, what couldn't it do? Rosenblatt was pretty clear-eyed about both. I mean, look at what it achieved. It learned from trial and error. It could generalize to new things, which we just talked about. Its memory was distributed, which is a cool way of saying that no one little part held one specific memory. It was spread out all over the network. That's a lot like our brains. It could even learn to recognize sequences, like sounds, not just pictures. This was huge. It proved that a simple brain-inspired network could do some seriously complex stuff. But Rosenblatt knew its limits. He was very upfront about it. A perceptron could look at a shape and tell you that's a square. Easy. But it could not look at two shapes and tell you the triangle is to the left of the square. See the difference? That requires understanding the relationship between things, a whole other level of abstraction. And his simple design just wasn't built for that.
So let's bring it all home. Why are we talking about this machine from 1958? Why does it matter now?
Because this right here is the fundamental idea behind pretty much all modern AI. The idea that a network of simple little units can learn to see complex patterns just by tweaking the strength of its connections over and over again. That thing Rosenblatt called value, today we call it weights. And adjusting those weights is exactly what happens inside the massive neural networks that power everything from your phone's camera to the large language models that are changing the world. It's the exact same core idea. Just let that sink in. 1958. The core concept behind the AI revolution we're living through was figured out and published on paper all the way back then. The Perceptron wasn't just a clever machine design, it was a whole new way of thinking about what intelligence even is. You know, Rosenblatt saw the limit of his machine was understanding relationships. And that's exactly what today's AI is just starting to get good at. It really makes you wonder, doesn't it? If a simple machine from 1958 could learn to see, what will the vastly more complex systems of tomorrow learn to truly comprehend?